everybody, welcome back. This is Math 35, College Algebra at College of the Sequoias. So we recently finished our review chapter. Now it's time to start digging into some algebra. Chapter 1 is on equations and inequalities. And inequalities. And this first section I'm doing is 1.1. 1.1 is linear equations, or linear equations, literal equations. So let's start off. Let's just talk about what an equation is. An equation is a statement with variables and constants that show two sides are equal to each other. Solutions to equations when substituted in for the variables I'm going to say variable or variables if we've got more than one, make the statement a true statement. True where each side equals the other. Good thing to know. It's a little blurry, isn't it? Do autofocus. There we go, that's less blurry. Equation is a statement with variables and constants that show two sides are equal to each other. Solutions to equations when substituted in for the variables make the statement true where each side equals the other. Important to note, equations have equal signs. If you see an equal sign, it's an equation. Generally, we have a variable or symbol in there that we don't know the quantity for, and we're solving for it. I could have something like x plus 3 equals 4. Or I could do x plus 6 equals 7. And note, if I let x equal 1, then the left equation becomes 1 plus 3 equals 4, which is true. Turn that off. And if I do it over here, plug in 1 plus 6 equals 7, which is true. And I tend to do a little check mark above the equal sign that shows, yes, it made a true statement. I was checking to see if it makes a true statement, and it does. So the proper notation the solution set is bracket 1. curly braces. More than one solution is separated by commas. You saw this in set notation. By commas. Okay. Now, notice these equations both have the same solution set. You need that pause to write down. Please pause. These equations had the same solution set. Which we call equivalent equations. And how does it make them equivalent? Versus x plus 6 equals 7. Notice if I add 2 to both sides, or 3 to both sides, on this left equation, well, I have x plus 3 is x plus 6. 4 plus 3 equals 7. And notice they're the same. Now they are equal. Now they are identically equal. So that's why we call them equivalent equations. You can rewrite one of the equations in the form of the other. So, fun fact, the largest exponent on a variable reveals the maximum number of solutions. If we have just like here, x or x to the first power, just one solution, and we saw that it was just one. We have x squared, we have at most two real solutions, or two solutions. And I'm going to add the word real in. We may have complex solutions as well. That's another chapter, another section. Notice what I did here. I added 3 to both sides. If you can do that, this is one of the properties of algebra. So maybe I'll do this on another page. We have the addition and multiplication properties of equality. So the addition one, if A equals B, then A plus C equals B plus C. What this means is we can add or subtract the same value from both sides of an equation, from all sides of an equation, and maintain the equality, still remains equal. And we also keep the solution set. Maintain the equality and solution set. The multiplication property, very similar. Again, if A equals B, if the left side of the equation equals the right side of the equation, then I can multiply both sides of the equation by the same value and they remain equal. We do have a single caveat. Don't use C equals 0. It destroys everything you've got. Now everything is equal. You multiply by 0, you end up with 0 on both sides. Of course, they're equal, but you've lost any information that you have. And this is the same thing. We can multiply, which means we can divide, because division is just multiplication of the reciprocal. Both sides of the equation by the same value. Multiply by both sides of the equation by the same value and maintain equality. The equality and solution set. Okay. So let's just start off with an equation in one variable. An equation in one variable, let's do ax plus b equals 0. And a does not equal 0. If a equals 0, then b has to equal 0, and this is a pointless statement. The example I gave earlier, x plus 3 equals 4. Maybe I should write this as ax plus b equals c. We can always end up writing it as ax plus b equals 0, but the idea here is the goal or the way to solve an equation is to isolate the variable. And when I say solve an equation, what I mean is find the solution set. Is to isolate the variable. I'm off the screen. Okay. You're a pack of wolves and you're trying to get the elk by itself. That's a little gruesome, right? So how do we do that? X plus 3 equals 4. We're going to use the properties we just had. Use the addition and multiplication properties. If I want to get x by itself, I really need to make that 3 on the left side equal 0. So I can add its opposite. And if I add its opposite on the left side, I have to add its opposite on the right side. If I do that, you should be able to bring the equal side down. Both sides have the same action. Same operation on both sides. Your equal sign comes down, and 3 plus -3 is 0, and we're just left, that says x plus 0 equals 4 plus -3 is 1. And when you're adding 0 to anything, it doesn't change its value, x equals 1. And that was our solution set. X equals 1 is the solution. In set notation, it's like that. A lot of people, this is the proper way. Most people accept this. Actually, they say x equals 1. Okay. So, whatever we do, perform operations on both sides. Identical operations. Do the same thing on both sides. With the aim of getting the variable alone. And that's what isolation means. If you isolate it, it's alone. Okay. So that x plus 3 equals 4. I did adding the opposite. I added the opposite above. And the reason why I phrased it that way is you want to do the opposite action. Do the opposite action. Alternatively, rather than just adding 3, right now I have add 3. The opposite of addition is the opposite of adding something to an object is to take something away. We could subtract. So adding a negative number or subtracting the same number is the same thing. We end up with x equals 1. But this idea applies to all of it. Do the opposite action. Do the opposite actions starting with addition. And do addition, subtraction before multiplication, division. And I'll show you what I mean in a second. Let's just get the ground rules up. All right. So that's an addition example. Let's look at a multiplication example. I've got 2x equals 5. Now, let's even do better. Let's go 3x equals 7. So right now, x is multiplied by 3. The opposite action would be division. Or multiplication by the reciprocal. So I'll show that both ways. If I divide both sides of the equation by 3, divided by 3, these cancel out and leave behind a 1, and I'm left with x equals 7 over 3. Alternatively, I can multiply by the reciprocal of 3. 3 is the same thing as 3 over 1, so I'm going to multiply both sides by that value upside down, 1/3. Again, things on top and bottom cancel out, and I'm left with x on the left side. And on the right side, 7 times 1 is 7, 1 times 3 is 3, 7/3. Note, the answer doesn't have to be pretty or nice. Pretty, nice, or simple. It just has to solve the equation. One of the best things about mathematics is you can verify your work. Check your work to show that it's true. And we do that by substituting the solution in for the variable. So I had 3x equals 7. I'm going to substitute the solution in. The solution, I'm going to put it in parentheses, 7/3. Is that a true statement? Put a question mark above the equal sign. To indicate you're checking your work. So when I substituted x or 7/3 in for x, I put a little question mark sign above the equal sign because I'm not saying it is true. I'm checking to see if it's true. If it's not true, I got the wrong answer. Okay. Well, I'm going to rewrite 3 as 3 over 1. And when I multiply, 3's cancel, and I'm left with 7 over 1 on the left. And that does equal 7. That's a true statement. So I'll put a little check mark. Check mark indicates it's true. Other people do this. It's not a rule in mathematics, but it's common practice, let's say. And you might be asking, well, what if the division looks like it was easier? I didn't have to work with fractions. Why multiply by the reciprocal? Let me show you. Sometimes division sucks. What if I had let's do 4/3 x equals 12. Dividing by 4/3 sucks. Instead, multiply by the reciprocal. I'm going to take that 4/3 and I'm going to flip it over, and I'm going to make that 3/4, and I'll multiply both sides by 3/4. The 3's cancel, top and bottom. The 4's cancel, they leave behind 1. And what I'm left with is x on the left. If I make this 12/1, 12 is 4 times 3. I'm going to just substitute that in so I can cross off what I need. I can cross off 4's now. There's a 4 on top and bottom. It's replaced with 1's. And I'm left with 3 times 3 on top, which is 9/1, x equals 9. Now, if you're not comfortable doing, I hope you get comfortable working with fractions that way. I will show it where you just work it out though. We multiply by 3/4. You multiply numerator and denominator separately. 3 times 4 is 12. 4 times 3 is 12. And then 12 times 3 is 36. 1 times 4 is 4. And now 12 divided by 12 is 1. And 36 divided by 4 is 9. Again, x, we don't need the 1, because 1 of anything is just that object, so x equals 9. Does it work? Check. 4/3 x equals 12. I'm going to substitute in my 9. Maybe I'll make it 9/1 because I've got fractions there. Does that equal 12? 4 times 9 is, what did I do here? Yeah, 4 times 9 is 36. The bottom is 3 times 1 is 3. Does that equal 12? 36 divided by 3 is 12. So it works. So x equals 9, or we'll do the curly braces 9. So it's important to note, solutions don't have to be pretty, they just have to work. Now, you might be familiar from high school or elementary school or junior high. Answers often were very simple answers like 5 or 6 or 10. They did that to make showing the operations easy. It's easier to follow what's going on. But in reality, usually we don't end up with whole numbers or integers. Most numbers in reality have fractions or decimals. So it doesn't have to be pretty, it just has to work. That is probably going to be one of the hardest things that you need to accept. It took me a while to accept, and I like math. So something else I want to show you is when you're checking your work, if you check your work, and it doesn't make a true statement, your solution was wrong. And go back and redo the problem. I'm going to go back to that example I just gave. So I had 4/3 x equals 12. We know x equals 9 is correct. What if I solve this and got x equals 8. In the check, let's do the check. Four-thirds x equals 12. I'm going to substitute 8 in. Do 8 over 1. 4 times 8 is 32. The bottom is 3. Does that equal 12? Three goes into 32. How many times? We got a 1. And it goes in 0 there. We've got a 2 remainder. This is 10 and 2/3. 10 and 2/3 does not equal 12. Okay? X must not equal 8. Go back and resolve it. That is one of the biggest problems I see with students that check their work. They don't get the right answer and they plug it in and it gets some mumbo jumbo that doesn't work. And rather than assuming that their answer's wrong, what they do is they like kind of fudge it and then they just lie. Students will do this. Students will go from here, some students I should say, some students go from there to there and go 12 equals 12. Yes. Well, no, that's not true. This does not equal 12. You can't force it to work. If the answer doesn't work, it doesn't work. Okay? Just make sure you go in and check your work and then just resolve the problem. Or go back and do step by step and figure out where you went wrong. It might have been something as simple as a dish you added wrong. You might have missed a negative sign when you needed it. Those are 2 common mistakes. Let's see. So this was nice and simple. Let's just make it harder. Let's go big. Let's do, so the objective here, solve. I'm going to do -4 times 3x minus 5 equals 3 minus parentheses 8x plus 7. Okay, the parentheses are a problem. We want to deal with the parentheses first. So I'm going to distribute to get rid of the parentheses. And distribute to remove parentheses. If I distribute here, I've got -4 times 3x is -12x. And -4 times -5 is +20. The 3 doesn't have a parentheses. I'm going to bring it down. This 3 minus parentheses 8x plus 7 minus that is kind of like saying -1 times that. So what I'm going to do is distribute a -1. -1 times 8x is -8x. -1 times 7 is -7. Then combine like terms. Well, the left side doesn't have anything alike, so I'm just going to copy it down and leave it alone. The right side, though, I've got 3 and -7. Those combine to make -4. And we tend to write the variables first. So I've got -8x minus 4. Then get all the variables on one side. Get all the variables together. And we have to use that addition and multiplication properties to do it. I can't just combine them because there's an equal sign in the way. The equal sign is like a boundary. You can't combine objects from opposite sides. So rather than adding the negative 12x and negative 8x, because there's a boundary between them, what I got to do is do the opposite. So what I can do is I can add 8x to both sides. Or I could have added 12x to both sides. I'll go back and do this showing the other way in a second. If I add 8x to both sides, negative 12x plus 8x is negative 4x. And then I still have plus 20. On the right side of the equation, minus 8x and plus 8x go away. I'm left with minus 4. Now, I told you that when you have it something like this, I've got all the variables together. Addition before multiplication. The additive property or addition property before multiplication property. So here I've got plus 20. It's like having 20 extra pounds. I want to lose 20 pounds, so I'll subtract 20 pounds from both sides. If I do that, 20 minus 20 is 0 on the left. I still have the negative 4x, so that's what's on the left. On the right, negative 4 minus 20 is negative 24. Now I can do the multiplication or division. Don't forget the negative sign. If I divide by 4, I don't have enough. It would be negative x. I need to divide by negative 4. And if I do that, the negative 4's cancel, and I'm left with x on the left. On the right side, the negatives cancel each other out. 2 negatives make a positive. 24 divided by 4 is 6. Okay? We'll check that in a second. I want to show you the other way. I added 8x. If I add 12x, let's see what happens. Instead of 8x. Let's go back up to negative 12x plus 20 equals negative 8x minus 4. Now here I'm going to add 12x to both sides. And on the left side, I'm just left with 20. On the right side, I have 4x minus 4. I can add 4 to both sides. And I get 24 equals 4x. And I can divide both sides by 4. And 24 divided by 4 is 6. 4 divided by 4 is x. 6 equals x. These two things mean the same thing. Now, why would I do it this way? Some people don't like having the x on the right. But notice what happened. By moving the 12x, I ended up with a positive 4x rather than the negative 4x I had up here. That is the preferable way. The reason why is it's easy to lose that minus sign, especially if you have a fraction. Sometimes that minus sign looks like part of the fraction bar and you just lose it, you lose track of it, and your answer ends up being wrong. By making it so that I resulted with a positive 4x by moving the 12x, I make sure I don't have the mistake of dividing by forgetting to divide by a negative number. There's no negative here to worry about. Both solutions work, both methods work. Please use the one that works best for you. Note that these two are equal though. Okay? They don't have to be pleasant. Let's do 3x plus 6 over 10 minus 1/2 x equals 2/5 x plus 33 over 5. God, that's miserable, isn't it? It's miserable looking, right? I made it miserable looking to make you want to see what I want you to see. We have all these fractions. What's making it miserable? All those fractions, right? Screw fractions. Get rid of them. Don't work with the fractions. Screw them. Let's get rid of them. And we do that by multiplying by the LCD. Both sides by LCD. Least common denominator or lowest common denominator. All right, so what is the lowest common denominator? My denominators are 10, 2, and 5. And if I factor them, 10 is 2 times 5. 2 is already prime, and 5 is already prime. I'm doing the table I showed you before. And the columns make the LCD. LCD is 1 from each column. 2 times 5 is 10. I'm going to multiply both sides of the equation by 10. We got to distribute. So when I distribute the 10, I'm going to do it. And the reason why I'm going to do it, I'm going to show this. I'm not going to multiply it through. I'm going to show it like this. I've got 10 times 3x plus 6 over 10 plus, or minus, that's a minus sign there, minus 10 times 1/2 x equals 10 times 2/5 x plus 10 times 33 over 5. I can do some canceling. The 10s there cancel, and I'm left with 3x plus 6 there. Here, 10 is 5 times 2, and the 2's cancel, and I'm left with just 5. Minus 5, and there's an x still, minus 5x. And on the right side, I can do the same thing. 10 is 5 times 2 in both circumstances. The 5's cancel with the denominator. And I'm left with 2 times 2, which is 4x, plus 2 times 33 is 66. Okay? So it's easier, rather than distributing the 10 to the 3x and the 10 to the 6 and simplifying there, simplify right now. Now we'll combine like terms. I've got a 3x and a negative 5x. That's going to give me negative 2x. And I still have plus 6 on the left. The right side, nothing combines. Now I've got variables on both sides. I need to get the variables together on one side. So I'm going to add such that my variable has a positive coefficient. or that's the number in front. So let's just think about it. If I subtract 4x from both sides, negative 2x minus 4x is going to give me a negative 6x. I don't like that. I will usually try to move the variables to the left. I like having the variables on the left also. But if it ends up with a negative number, fuck that. Don't do it. So instead of doing that, I will move the negative 2x by adding its opposite, which is positive 2x. And I got 6 equals 4x plus 2x is 6x. And then I still got plus 66. I subtract 66 from both sides. I'm doing the opposite of what's there now. And I start with the addition or subtraction. And I get negative 60 on the left, 6x on the right. Finally, I divide by 6. And the right side is just x, the left side is negative 10. They call these conditional equations. I'm sorry. This was a conditional equation. What they mean by that is the condition for it to be true is that x must equal negative 10. I don't use the phrase conditional equation. Math lab might ask you about it. You're not going to hear it a lot, but I thought I'd better give you the terminology just in case it pops up. Okay? So let me give you one to do. Well, yeah, I'm going to give you one to do. 10 plus 14x equals 7 times 2x minus 5. So solve and check your work. So I would pause it and try to work that out. See what you come up with. I'm going to assume you paused it. The first thing you should do is get rid of those parentheses signs. So I'm going to distribute the 7. 7 times 2x is 14x. 7 times negative 5 is negative 35. Now, if I try to get all my x's on one side, it doesn't matter which one I move, I'm going to have to subtract 14x. And what I end up with is on the left, I have 10. On the right, I have negative 35. 10 equals negative 35. That's false. This is false. And it doesn't really matter what x is, because it canceled out on both sides. There is no solution to this equation. You will see the terminology. You'll see contradiction. No solution. they might say empty set. An empty set you can depict as empty braces or a 0 with the bar through it, but don't put just 0. It's got to be that this means empty set. This means 0. 0 can be a solution. If 0 is a solution, it's not empty. Another thing they use is they'll say does not exist, or solution does not exist. And folks abbreviate that DNE. That was a tricky one, right? There was nothing to check. I threw you a curveball. That's how I roll. Here's another curveball. You've been warned. It's a curveball. Solve this. Look at me using sports analogies. I don't even like baseball. It's fun to go to a game with you if you're with friends and you're hanging out, you have a hot dog, and every once in a while you hear the loud thwack as the bat hits the ball. You look up to try to see the ball, but you're in the nosebleed. You can't see where the ball went anyways. Baseball games are really just a way to hang out with your friends. So try solving that. I'll assume you paused it. -3 times 2x is -6x. -3 times -1 is +3. I still have +5x equals 3 minus x. I combine like terms. -6x plus 5x is -x. I still have +3 equals 3 minus x. Now, if you recognize it right here, you can stop as well. But if you don't, let's add x to both sides. And if I do, the x's disappear on both sides, and I get 3 equals 3. This statement is always true and doesn't depend on x. So any x value works. Since any x value works, I could plug in x equals 0. I could plug in x equals 1 billion. I could plug in x equals pi. And this is going to work no matter what. There are an infinite number of solutions. That's one way of saying it. They also say x equals any real number. And they might use that. That's the notation for a real number, or the solution set notation. And what this is called is the identity. So that when it doesn't work at all, it's called contradiction. That didn't show up very well. When it did it again. If the statement makes a false statement, it's a contradiction. If the statement makes a true statement, no matter what x, it's an identity. All right. Onward. So if we have more than one variable, they call these literal equations. I'm not sure why. Common ones you'll see, well, you'll have like y and x in there. In fact, we're going to see that equation again later. So you have more than one variable. Oftentimes it's just two, but you can have more. And generally the idea is to solve a literal equation for one of the variables. It may help to pretend the other variable or variables are just numbers, but you don't have to. So let me give you an equation that shows up in physics. Ooh, he's throwing physics at us already. Yes, I am. Example. This is a common equation. D equals RT. D is distance. R is rate of movement or speed. And T equals time. This is usually solved for R. We'll pretend T is just a number. And D also. So I've got D equals R over T, or R times T. I'm going to pretend T is a number. Like, let's say T is 2. I've got R times 2, or 2R. What would I do if it were 2R? Divide by 2. So, but it's not 2, it's T. So instead, we'll do it the same operation though. Instead, we divide by T. On the left side, I've got D over T. On the right side, I just have R because the T's cancel. Rate equals distance over time. And you know this, you've heard this. If you haven't heard this, you've never traveled anywhere, not even in a car. MPH, miles per hour. Is the number of miles over 1 hour. Miles is a distance. That's a time increment. Distance over time. And the rate is your speed. How fast are you going? We don't necessarily have to solve for R though. What if we're just trying to, we know how fast we're going. Let's give this example. What if we know how fast we're going? How fast and how far we are going. Then the only thing we don't know is for how long. So I could solve that for t. D equals r times t. If I solve for t, I will divide by r. T equals d over r. Disneyland is about 200 miles away. And your Uncle Miguel averages 50 miles per hour driving there. Yeah, he's probably going faster down the 99 until he hits the Grapevine. He might even be going quick through the Grapevine. But when you get into Los Angeles and if you're anywhere near daytime traffic or rush hour traffic, stuff slows down. You're averaging 50 miles an hour. How long does it take to get there? To get to Disneyland. Well, my distance, what do we have here? Distance is 200 miles. And I've got rate. Rate is 50 miles per hour. And so I can use the t equals d over r. 200 over 50, which is 4. For what? Turns out it's 4 hours. How can I find that it's 4 hours, though? How do I know it's 4 in hours? I got 4. I got rid of the terms. Let's go back and write this the way it is. I've got 200 miles over 50 miles per 1 hour. Now I've got a complex fraction. The way you deal with complex fractions is you multiply top and bottom by the reciprocal of the bottom. So I'm going to multiply the bottom by 1 hour over 50 miles. I'm going to multiply the top by 1 hour over 50 miles. And the reason why we do that is everything on bottom cancels. 50s cancel, miles cancel, hours cancel. Everything just leaves a 1. The bottom is 1, which is going to go away. So I get t equals 200 miles times 1 hour over 50 miles. I could put the 200 over 1. Miles cancel now. And even if I don't simplify yet, I've got 200 over 50 hours. 200 divided by 50 is 4. So it may be a good idea to write down your units, the units of measurement that you're using when you do these problems. Okay? It can be a little more complicated. Let me show you a little more complicated one. S equals KR squared plus KRT. and we'll solve for k. Now, this looks like it can be confusing. But what if r and t are numbers? Then this is just a number times k. And this is a number times k. If I had 2k plus 3k, what would I do? I would add the 2 and the 3 together. What you're really doing there is, so let's show the equivalent example with numbers. If this were s equals 2k plus 3k, we know that would equal 5k when you add them together, right? What you're really doing is you're factoring out the k. We've got 2 plus 3 in parentheses. That equals 5k. So we factored out the k. Let's apply that to the one we had above. If I pull out the k, the first thing I just have r squared left. The second one I have rt left. And then note, what will we do here? Then divide by k's multiplier. I'm going to say it that way rather than using coefficient. Because right now, what k is multiplied down here is different than what's here. Here I would divide by 5. So here, instead of it being 5, I'm going to divide by r squared plus rt. And I get s over r squared plus rt equals k. That's solved for k. All right. It doesn't have to just be something like that. Let me give you what guys want to try, and then this lesson will be done. So solve for y. You're going to have 11y plus 8 equals 2 times 4y plus 5w, that's in parentheses, and then we have minus 60. All right. I'll assume you paused it. The first thing you needed to do is distribute. Bring down everything else. Make sure you're copying down everything that you haven't touched. Because if you don't, and you just write down what you multiplied out, you're gonna lose track of information. And I can tell you honestly, when I walk around with C students, about 90% of students just don't write down this. They just write down what I'm about to write here in red. 2 times 4y is 8y, and 2 times 5w is 10w. And they'll leave the black stuff off. If I had this, they'll do something like that. And then they'll try to connect the dots with what was going on up above, and that's confusing. Don't do that. Recopy down everything that you haven't touched. I did it in a different color, so it's easier to track what I edited. or what I moved. Now I want to solve for y, so I'm going to treat everything else like numbers. So w's a number, 6z's a number. I can't combine them because I don't know what their numbers are, but they're numbers. So I really have y's on both sides. I want to get my y's together. I'm going to move y's so that I end up with a positive coefficient on y. If I move the 11y, it would have to subtract 11y. 8 minus 11 is -3. I don't like that. So instead, I'm going to move the 8y. And if you're comfortable, I know I'm going to end up with 3y over here. I could do the +8 and then do another line. If you want to save yourself some effort, you know you're getting all your y's on your left. Why don't you move all the other numbers to the right at the same time? I'm going to subtract 8 at the same time. And I didn't put it underneath the w because I want to make sure I don't combine it with anything that I don't know. I can't combine the 10w and the -8 because this has no w's. So the y's would go away, and I'm left with 10w minus 6z minus 8. Finally, I would divide both sides by the coefficient on y, and I get y equals 10w minus 6z minus 8, all divided by 3. And when the numerator, the top has plus or minus signs, you can break it up into different fractions. Or y equals 10/3 w minus 6/3 z, which is 2, minus 8. Either works. Either is true. What they ask for in math lab, they'll hopefully tell you. And that's it for 1.1. All right. 1.2 is a bunch of word problems. I've made it extra credit. I strongly encourage you to do it. Because let's face it, math in reality is word problems. That's the only way math shows up in real life, is word problems. When numbers just don't exist in free float in midair, we're always solving some real life scenario, and that has numbers in it. That's 1.1. I'll be doing 1.3 shortly. That's on imaginary numbers or complex numbers. Until then, peace out.